Hi everyone, I am Miss Hu, your physics teacher. In this video, we are going to go through the concepts of electromotive force and internal resistance. What we'll be covering in this video are what is electromotive force and internal resistance, the equation relating electromotive force and internal resistance, as well as interpret the VI graph to obtain electromotive force and internal resistance. Now, first of all, let's go through the definitions. So as written on this slide over here, as you can see, we have the definitions of both electromotive force and internal resistance. Let's start with the EMF first. Now, EMF, which is short for electromotive force, let me just add that in. So electromotive force is basically the energy transferred or work done by an electrical source to move 1 coulomb charge around a complete circuit. If you have learned about potential difference before, you might find that the definition seems to be rather similar, but of course there are some differences. Now, if you're like, I can't remember what's potential difference, well, I have the definition written right here on the right. Potential difference is the work done to move 1 coulomb charge between 2 points in a circuit. To illustrate the difference between EMF and PD, which is potential difference, let's look at the circuit over here. So we have over here the dry cell, which is our power source. So based on the definition of electromotive force, it is the energy transferred or work done by an electrical source, which in this case is the dry cell, to move 1 coulomb charge around a complete circuit. Now, if you recall, when current flows, it's also basically charge flow. So electromotive force refers to the work done by the power source, by the dry cell, to move 1 coulomb charge around the entire circuit. Potential difference, on the other hand, refers to the work done to move 1 coulomb charge between 2 points in a circuit only. For example, if we want to look at this light bulb with this voltmeter, then the potential difference referred to is the work done to move the 1 coulomb charge between these 2 points only. Now, if you recall, potential difference is actually a type of voltage, which means that electromotive force is also a type of voltage. And that's why sometimes it can be quite confusing to students because it's a bit of a misnomer. But when you look at electromotive force, you thought, oh, it's a force. It should be Newton. Nuh-uh, you got fooled right there. Electromotive force is actually a type of voltage, just like potential difference, which means that the unit for electromotive force is voltage. So I'm going to write that down over here. So electromotive force is actually measured in volts. I thought I had changed it to normal, and apparently I didn't. So I'm just going to fix that. That's actually in volts. Now, this is the equation based on the definition, where it relates the electromotive force with the energy transferred or work done to the amount of charge flowing. So electromotive force is the energy done per unit charge that's flowing. That's why the formula is EMF equals to E over Q. So E is written a little bit differently here to differentiate it between electromotive force and the energy transfer. When you look at the formula for potential difference, it looks pretty much the same as well, right? Because if you look at it, it's kind of the same thing, right? Potential difference, in this case, which is V, is also the work done or energy transferred to move a unit charge between 2 points. So formula-wise, they look identical. The difference here is from which point to which point. So you would calculate potential difference based on a work done between the 2 points that we're looking for only, whereas electromotive force is across the entire circuit. So this formula, because I took this from one of the textbooks, it doesn't have the units written, so I'm just going to add the units here. Okay, energy transferred or work done is measured in joules, while charge is measured in coulomb. So this also means that voltage, let me fix that. Okay, which essentially means that volts is essentially joules per coulomb. Right? So don't need to fret so much about the formula, right? Because it's essentially just based on the definition. Now, internal resistance, on the other hand, refers to the resistance caused by the electrolyte in the dry cell. Okay, what does this mean? Now, if you recall, dry cells, and you should have learned this in chemistry if you took chemistry, right? Dry cells use chemical reactions to produce the electrical current. And anything that conducts electricity or completes an electrical circuit will always have resistance. The problem here is that the dry cell is a power source, and within the dry cell, there's also resistance, which means that the current has to overcome its own resistance before it flows out into the circuit. So because the resistance is inside the power source itself, we refer to this kind of resistance as internal resistance. And you might find that occasionally the term external resistance is used in certain questions. External resistance refers to the resistance outside the dry cell, anywhere outside the total, outside the dry cell. Okay? So to help you get an idea of what electromotive force and internal resistance mean, you can think of it this way, right? So electromotive force is just the voltage of the battery. Now, you cannot write this as a definition. You can't say, oh, electromotive force definition, voltage of the battery. You cannot do that. The actual definition must always follow the scientific terms that are used. So that's why we have to write this as our definition for electromotive force. So remember that scientific definitions have to be written in a very technical, accurate way so that there's no dispute or misunderstanding with regards to that particular term. This is merely for your understanding. So it's done in a very layman way, just for you to, okay, have a rough idea of what this electromotive force is. So an example of this in real life would be like, okay, if you get an AA battery, like how much is the voltage? Okay, most of my students get this wrong the first time. AA batteries have voltage of 1.5 volts. So that's the electromotive force of the battery. Whatever that's labeled on the battery, whatever voltage that the battery provides, that's the voltage of the battery. That's the electromotive force of the battery. So internal resistance, in simplified terms, is quite simply the resistance inside the battery. And this resistance, where does it come from? It comes from the electrolyte in the dry cell, inside the battery. So now that we have a clearer understanding of what electromotive force and internal resistance are, hold on. The unit of internal resistance. Now, internal resistance is quite simply a type of resistance. So the unit for internal resistance is ohm. So I'll write the unit over here. I'll just put this in bracket. Okay, we use the omega symbol, which is the short form for ohm when we write our answers out in physics. So that's the unit for internal resistance. It's the same as resistance. All right, so now let's look at the concept of electromotive force and internal resistance first before we look at the equation. All right, so let's look at the diagram on the left first. Now, we have a situation here where we have a circuit connected to a light bulb. We've got the voltmeter across the terminals of the battery, but as you can see, the switch is open. Now, let's say, for example, this particular battery has electromotive force of 3 volts written on the battery. Now, how much do you think this voltmeter would show? So most of my students, when they're learning this for the first time, they'll tell me, oh, it's 0 because, it's an open circuit, the circuit's not complete. So don't worry, that's a very common mistake, a very common mistaken assumption that's made. It's actually not 0. When you place a voltmeter across the battery, now, if the circuit is open, it means there's no current flow through the light bulb. So you can imagine as if this circuit is not actually there. So basically, the voltmeter is actually measuring the voltage of the battery, correct? So the voltmeter will actually show you 3 volts. So I'm going to write that down here in green. It's actually going to show you 3 volts. Now, let's say exact same setup, but now we close the switch. Now, most people would think, okay, the voltmeter should show you the same voltage as well, because now it's a complete circuit, right? In reality, we find that the voltmeter reading will always be less than 3 volts. Okay, and why is that? Because of internal resistance inside the dry cell. So what happens is some of the voltage of the battery was used to overcome its own internal resistance, and as such, the voltmeter reading actually drops. So how much? It really depends on the condition of the battery. The longer you use a battery for, the higher its internal resistance becomes. The electromotive force of a battery never changes during its lifespan, but how much voltage it can produce to move that 1 coulomb charge across the entire circuit depends on how much internal resistance it has. So the older the battery, the more you've used it, the longer you use it for, then because it's gone through more chemical reactions, a lot of chemical reactions to produce the current, then the higher the internal resistance is, and then the lower the voltage provided would be. So I'm just going to write here, it's going to be less than 3 volts. Right? So if you come across a question where it says negligible internal resistance, then you can assume that there's no internal resistance, the value will always be exactly the same as the original. But for the purposes of this video, we're going to go through the concept of internal resistance, because you will come across questions where the internal resistance is not negligible and you need to know how to get that value. So let's look at the equation. Now, before we get into the electromotive force equation, let's first try to recall what we do understand about potential difference. So over here, we have a very simple series circuit. If you can recall what you've learned about voltage and potential difference, you can see that, okay, over here we've got 2 lamps in series. The potential difference, the total potential difference across the entire series circuit will be the sum of both of these potential difference. So I'm going to write it here. V is actually equal to V1 plus V2. This makes sense, right? So this is what you have learned in series circuits. Now we're going to take this and apply it to what we understand about electromotive force to obtain the equation. So over here, now, what is this? Okay, we have a very simple circuit here, and I want you to imagine now that inside the dry cell, there's actually internal resistance, right? So to help you visualize, we've got this little baby resistor over here that will represent the internal resistance of the dry cell. So just to help you visualize this a little bit better, we're going to enclose this entire thing into, okay, a little rectangle. Let's say this entire thing here is the dry cell. Okay, now in reality, there is no baby resistor inside the dry cell, right? It's the electrolyte that's creating the resistance. But for visualization, I want you to imagine that, okay, this thing is actually the resistance of the dry cell. Okay, so when we have a voltmeter placed here, this voltmeter, say for example in this case, it not even an example, it's for real. This particular voltmeter does not measure the potential difference of the dry cells. It's actually measuring the potential difference of the entire circuit from here to here to here, right? So this voltmeter is for the outside of the dry cell, so the entire external part of the circuit. Now, this particular blue voltmeter, made it smaller on purpose. I want you to imagine that this represents the voltage that we could measure of the dry cell. So, in fact, I should actually fix this by putting the voltmeter inside the dry cell. Now, of course, it's not going to be technically possible, but imagine that this little blue voltmeter is measuring the voltage or the potential difference of the dry cell of this tiny little resistor. Now, why are we doing this? Because if you can recall from the previous slide, we know that V is, the total V here is the sum of V1 and V2. So we're going to take that into this diagram now. So let's say this V is the external voltage, which is measuring the external resistance, the potential difference across the external resistance. So right here, external, while the blue one represents the internal voltage across the internal resistance of the dry cell. Now, electromotive force is the total work done by the dry cell. So it's a total voltage of the entire thing. So I'm going to write this way. So the curly E represents electromotive force, right? So the E here, oh, that looks terrible. Let's try that again. So E basically represents the external V, all right, this is really big, plus the blue V, which I'll write as a smaller V over here, just to make it clear. Okay, this is the external V and this is the internal V. Now, of course, in reality, this doesn't actually exist. So we're going to write a proper equation out of this. Let's recall what we have learned in an earlier topic about circuits, Ohm's law. Now, based on Ohm's law, the formula that relates current, potential difference, and resistance is R equals V over I. I'm going to write it this way, V equals IR. And what we'll do is we'll take this and apply it into this equation. So I'm going to keep V as V first because we're going to see the proper equation after this. But we're going to focus more on this small v. So this small v here, you can also use Ohm's law to expand on this. So this time, let's say the internal resistance is represented by the small letter r. The potential difference across the internal resistance can be written with the formula I small r, where small r represents the internal resistance. This cannot be measured, obviously, but we can calculate this because we can get the current if we have an ammeter, and you can actually calculate the internal resistance of the dry cell. So this is how we can expand this, imaginary, non-existent internal voltmeter reading. All right. So this is an equation we can use that relates electromotive force and internal resistance. Another way to write this formula is to actually open up V with Ohm's law. That means we can write this as IR plus I small r. So if some of you be like, oh, look, we can, factorize this as well. Okay, go ahead, factorize it as well. You've got R plus R. So this is why you might find that in some books, they've written 3 different formula for electromotive force. If you look at it, they're pretty much the same thing. So yes, these are the equations that relate electromotive force and internal resistance in a circuit. I'll just write here at the side what these represent. We use a different color. So there's no space here, somewhere on top here. E is basically EMF, electromotive force, while small r is internal resistance. And there you go. So when solving questions involving electromotive force and internal resistance, you can use any one of these formula, depends on what information the question gives to you. Now, let's look at the graph. So if you conduct an experiment in the school lab to investigate electromotive force and internal resistance, this would be the setup of the circuit. So you need to have the voltmeter and the ammeter, of course, a fixed resistor and a variable resistor, also known as a rheostat in your school lab. And when you connect it, you place a voltmeter across the terminals of the dry cell. That means you're measuring the potential difference across the entire circuit. Okay. This might look similar to another experiment you may have done in the lab, which is based on Ohm's law, but there's a really big difference here. The voltmeter is placed differently, and we'll look at the comparisons between those 2 circuits shortly. In the meantime, let's focus on this particular circuit first. Now, if you conduct this experiment, the graph you're going to get when you plot a graph of potential difference against current, it will look like this. You'll actually find that it's a linear graph that is going down. That means it has negative gradient. So when you look at this, you're like, oh, okay. And you need to interpret this to obtain the value of the electromotive force as well as the internal resistance. Now, getting the electromotive force is very easy. Because electromotive force is the total voltage provided by the dry cell, correct? Which means that it has to be the maximum value of the voltage. Very easy. Whatever you get on the maximum value here on the y-intercept, that is obviously the electromotive force. But then how do you get internal resistance? So here's how we're going to get it. We're going to relate one of these equations to the graph, and we're going to take the first equation. So I'm going to write that. Let's use another color just to make it pretty. So we have E equals V plus IR. Now, we're going to borrow a concept from one of the mathematical topics, which is linear law. If you don't remember linear law or if you haven't learned it, don't worry, it's really easy. Okay, writing out this equation. This is an equation which you should know, that all of you would have learned in math. This is the equation for a straight line, a linear graph. Y is whatever's on the y-axis, M is the gradient of the graph, X is whatever's on the x-axis, and C is the y-intercept. What we need to do is we need to rewrite this equation into this form. So just to show you, okay, now we're going to have to make V the subject because V is on the y-axis. So I'm going to do this step by step so that you can see the process, all right? So let's keep V on one side and bring IR on the other side. So we have E minus IR equals V. And now we're going to swap the places here so that we get V on the left side. So V equals to E minus IR. But here's the thing. We want it to be written in this form where X is over here, the first one, and then it's connected to its M. So let's write one more line here. So V equals to, bringing I over here, R should be in front. We have negative R, now plus E. So if you look at these two lines, we look at these two lines, you should be able to see, let me combine that information here. You will have Y equals V, M is negative R, X is I, and C is EMF. So there you go. So the y-intercept here is the electromotive force, which matches what we have discussed just now, right? The maximum value of the voltage is the electromotive force. And the gradient here is the negative value of the internal resistance. If you're wondering why negative, you can look at the graph. It's going down. So that means the value of the gradient here is negative. So for example, if the gradient was negative 1, let me write it out here at the side. Let's use yellow example. If the gradient was negative 1, that means the value of the internal resistance here, see, M is negative R, right? So that means M, which is negative R, equals negative 1. That means R equals to 1 ohm. So basically, even though M equals negative R, because the gradient is negative, basically the negative values cancel each other out. The internal resistance would be positive in the end. So that's how we interpret this graph. So generally, you must know this, all right, that the gradient is negative R, the negative value of the internal resistance, while the y-intercept is the EMF. I'm trying to highlight these comparisons here in case you can't see. So these are the important things, all right? This is what you must know. Basically, you must know this and you must know this. So earlier, I mentioned the Ohm's law circuit, right? Let's look at the comparison now side by side. Okay, so we have over here on the left-hand side, the circuit where the voltmeter is placed across the entire circuit, whereas this one only has the voltmeter placed across one of the components, which in this case is the fixed resistor. You can see in both circuits that we have identical components. We have the voltmeters, we have the ammeters, we have the fixed resistor, as well as the rheostat or variable resistor. The difference here is the placement of the voltmeter. In the circuit on the left, the voltmeter here is measuring the potential difference across the entire circuit, which means that we're actually going to be measuring the terminal potential difference. The term terminal potential difference here means the potential difference of the circuit when we place a voltmeter across the terminals of the battery. So as the resistance of the variable resistor changes, the current will change, the resistance changes. Basically, it changes in such a way that the graph will have a negative gradient line. On the other hand, this graph is just measuring the potential difference across the fixed resistor. So as current increases, if the current increases, the potential difference also increases because the resistance doesn't change. So what we have here is you'll have a linear graph. Whoops, not exactly right. A linear graph that goes through the origin. So you get a directly proportional graph. So remember the difference here. This is a graph that is used to measure and obtain the electromotive force and internal resistance, right? The changing resistance here is what causes the graph to decrease like this. Whereas this one, the resistance here is fixed, so you get a proportional graph like this. Generally, from these graphs, okay, remember the y-intercept is the EMF, while the gradient is the negative value of the internal resistance. Whereas this graph, the gradient of this graph will give us the resistance of this component only. So be very careful when you are answering questions. Check where the voltmeter is, because that will tell you how the graph should look like. And that's it. So this is the overview of electromotive force and internal resistance. I hope you have found this video educational and helpful. Don't forget to subscribe for more lessons, solutions, and exam strategies from your physics teacher, Ms. Ho. You can also obtain more information at my website, physicsrocks.com. Happy studying!